we record the meeting.
Yes, yes, okay.
So, I need to wait a little minutes because the person will record it.
Okay, okay, okay.
James, when it is okay, you told me.
Iniciamos, profesor.
Okay, thank you. Graças a todos os que estão aqui nos ouvindo e tenho a satisfação de apresentar hoje professor Konstantin. Konstantin é professor da Universidade HSE de Rusia, Moscou. É especialista em supercondutividade e tem muito fácil e também em magnetismo. Tem muito ele chefe do laboratório em um grupo desta universidade, muito ativo cientificamente, e para hoje vai falar para nós outros sobre a quantum fluctuation em quasi-1D superconductors. Professor Konstantin, if you would like to introduce by yourself some things, you can do this, and after go ahead in your talk. Thank you very much in advance.
Okay, so I now switch to my presentation, and from time to time I will ask you some questions, because sometimes if the connection is bad, I continue to speak, but no one listens to me. Okay, so don't be surprised if sometime I will ask, is it okay?
Konstantin, usually you prefer, but if you prefer, sorry, your page is in loop. Okay, now it's okay. The question is done in the end of your talk.
Okay, okay, no problem. So I start. Well, definitely, first of all, I would like to thank the organizers of the conference who invited me here. I would like to thank Professor Mario Doria, who suggested me to participate here. I would like to thank personally Professor Isais de Oliveira, who invited me here. So the subject of my talk is presented here, and I will speak about quasi-one-dimensional superconductivity. Briefly, my scientific biography is the following. I graduated from Moscow State University, the Department of Low Temperature Physics. I'm an experimentalist. And already at the age of late 80s, beginning of 90s, I started to be interested in small dimensional superconductivity. Then for 15 years, I worked abroad in different European countries. And at 1915, I returned back to Moscow, where I share two positions. I'm professor of physics in National Higher Research University of Economics, Moscow, Russia. And also I have a laboratory in Kapitsa Institute, where I perform my low temperature and ultra low temperature experiments. So what the story is about? I think within, let's say, 15 minutes, I will make a very brief introduction to fabrication of narrow superconducting nanostructures, and a very hand-waving introduction to fluctuations in quasi-one-dimensional superconductors. Then the main part of my talk, about, let's say, 30 minutes, I will spend about physics, how it affects the behavior of these ultra-narrow superconductors. And last 15 minutes of my talk, I will probably speak about some applications which originate from this fascinating phenomenon. As it was announced, I will speak about one-dimensional superconductivity, but this is the subject which I was interested, let's say, about already 10, 15 years from now, and obviously many people contributed to the information I'm going to present to you. There was a generation of my students and PhD students. There is a permanent collaboration with theorists, and there are some discussions with various theorists and experimentalists who suggested some interesting points to share. Do you hear me? Hello?
Yes,
Hello?
Yes.
Okay. So, as it was written, I will speak about quasi-one-dimensional superconductivity. But going to the subject, first we have to discuss the issue of dimensionality. When one speaks about superconductivity, typically two scales are relevant. One is so-called coherence length, or in a very simple words, is the minimum distance on which superconductivity can be destroyed. And for majority of nanostructures I'm going to speak about, this is scale of about 100 nanometers. And another issue, less important for the subject of the topic, but nevertheless it's worth to mention, it's the field penetration depth, London penetration depth, which is also of about 50 nanometers. Both quantities are temperature dependent, and they diverge at critical temperature. Majority of science I'm going to speak about is applicable to ultra-low temperatures well below the critical temperature. And summarizing, I would like to say that nanostructures with characteristic diameter of a line width of about 50 nanometers can be considered as quasi-one-dimensional. So let us now speak about how dimensionality can affect properties of a superconductor. So the characteristic scale, as I told, for this physics is mainly the coherence length. So let us consider at this cartoon everything which is superconducting as green and everything which is normal in red. And let us first refer to the probably the most famous property of superconductivity, resistive transition, so resistance versus temperature. And first we will speak about at the top of the transition, when the majority of the system is still in normal state. The answer to the subject is known. It is called so well contribution of Aslamazov-Larkin. So inside a normal matrix, you will have fluctuating domains of superconductivity, which will reduce the resistance or increase electric conductivity, which will finally result for rounded top at the transition. And this affects both three-dimensional, two-dimensional, and one-dimensional objects. Now let us shift to opposite limit, to the bottom of the transition, when the system is mainly in superconducting state, but still here and there are fluctuations over normal phase. One should not be an expert in superconductivity, just basic electrotechnical knowledge is sufficient to understand that in this case, electric current will go along the green superconducting path, irrespectively whether we have there fluctuating domains of normal phase or not. So for three-dimensional and two-dimensional objects, the answer is that there will be almost no effect of these fluctuations. So this corner, bottom corner, will be very abrupt. But situation is dramatically changed when we have quasi-one-dimensional superconducting channel, where a single domain of a normal phase can completely block the supercurrent. And this is the subject of my talk. So a few words about fabrication of very small nanostructures. All over the world, and our lab is not the exception, very small nanostructures are typically made using electron beam lithography. So we take some insulating substrate, for example, glass, sapphire, silicon, or whatever. We cover it with polymer, special one, which is sensitive to optical or E-beam radiation. Then we irradiate particular plates, put it in some solvent, and the place where the radiation was applied dilutes easier, and finally we get such a mask which is shown here. And using some small tricks evaporating at different angles, one can fabricate quite sophisticated nanostructures, including nanostructures with tunnel barriers, so on, so far. So that is the traditional method. There is no innovation here. However, as I'm going to speak about some size phenomena, I should mention that nanofabrication has a lot of black magic. So you can fabricate the nanostructure one day using the same method as the day before, but it's absolutely different from the one. So keeping this in mind, we decided to develop a method which allows one to study the same nanostructure with reduced dimensions. And the simplest object which one can imagine to study is just a superconducting nanowire. So we used our E-beam technology, which is conventional, then study the sample, let's say measure resistance versus temperature, observe it also with electron microscope to check that there are no obvious artifacts, and then subject it to ion milling produced by low energy ion gun. So the energy is typically a fraction of a kilo-electron volt, and we also sweep the structure under the ion beam. Do you hear me well?
Yes, yes, yes.
Great. So what is obtained is shown here. These are IFM images of the same nanostructure, particular case aluminum. So on the left image, everything which is bright is aluminum. The blue surface is the original surface of the substrate, silicon. And after several sessions of ion milling, the cross-section of aluminum part is reduced, and reduced. But of course, we also etch the substrate. So finally, we get a wall out of our substrate on which we have a very, very narrow line, which is our metal. Also, please note that inevitably there are always some imperfections. And these imperfections are smoothed away while ion milling. This is the same effect if you take a rectangular piece of brick and throw it on a sandy beach. After some time, let's say 1 year, it will be not anymore rectangular, it will turn into some ellipsoid because sand polishes the sharp corners. So like this, we're able to reduce the cross-section and also to polish roughness. Very typical question when I present this method, whether it is invasive or not invasive. Everything depends on the kinetic energy of bombarding ions. If the energy is rather small, let's say half of a kilo-electron volt, then the penetration depth of argon ions inside a typical metal is smaller than 2 nanometers. And 2 nanometers for metals, we are speaking about like aluminum, titanium, or niobium, is just the thickness of few interatomic distances which is chemically destroyed. Meaning that our method is basically non-destructive. It cleans the very few atomic layers at the surface. And this is a transmission electron microscopy image of our nanostructure after etching. So here you see silicon substrate, and this is the cross-section of the nanowire made of titanium. And the very important feature that after several sessions of ion milling, we're capable of obtaining extremely smooth surface. For example, this is the image of titanium nanowire after several sessions of ion milling. We put then IFM tip on top of it, and we scanned the roughness of the surface. And the inset shows that roughness varies with accuracy plus minus 1 nanometer. And this corresponds to roughness plus minus 2 atomic layers. So the conclusion of this method is the following, that we can non-destructively and progressively reduce the cross-section of prefabricated nanostructures. And like this, we can go to really sub-10 nanometer scales, let's say 5-6 nanometers nanowires obtained from initially 50 nanometers nanowires. And this method is non-destructive and additionally provides extremely smooth surface shape. So this is the conclusion about fabrication. Is everything okay? Do you hear me?
Yes. Yes, okay, go.
So now I'm coming to
Hear you. Well,
to discuss their physics. The most famous property of superconductivity is sharp drop of the resistance at a temperature which is called critical temperature. This is the picture from a seminal paper of Kamerlingh Onnes, where first time he observed the superconducting transition of mercury. But at that time, no one thought about how the properties of superconductor depend on dimensionality. And as I promised, I'm speaking mainly about one-dimensional superconductors. So let us consider a long superconducting nanowire of cross-section smaller than the coherence length. So it is only one channel of supercurrent, meaning that either there is complete superconductivity or it is blocked by some fluctuation, and the length is much larger than both quantities. So such an object can be called quasi-1-dimensional superconductor. Then in the old textbooks of superconductivity, it is written that if one wants to destroy superconductivity in some volume, and in our case, the smallest volume has the extension of the coherence length, one should pay some energy, which is the condensation energy. And then theorists are capable to show that probability of such process depends exponentially on this energy required to destroy superconductivity within such a red spot, normalized by some energy. And the whole story is about what is this normalization energy. If to be sufficiently close to critical temperature, this is thus a thermal energy, kBT. But if to go at very low temperatures, the superconducting gap or superconducting order parameter is itself a quantum property, can fluctuate. And these fluctuations are mostly pronounced even at very, very low temperatures when the temperature tends to zero. If now to apply current to such a system where the fluctuations happen, it appears to show that there is a specific type of superconducting fluctuation. I will mainly speak about this later. When superconducting order parameter momentally zeros and the phase of the superconducting order parameter is changed by plus minus 2 pi. And this type of fluctuation is often called phase slip. Here is another, let's say, hand-waving explanation what happens. If to select some particular point in a nanowire and plot a dependence on free energy on the phase of superconducting order parameter, then there are two options from a system to go from one local minima to another. First is to go above the barrier, and this is the effect of thermal fluctuations, which is mostly pronounced in superconductors at high temperatures close to critical temperature. But as it is quantum system, there is a possibility where the system tunnels from one local minima to another. And this is the limit of quantum fluctuations, which is mostly the subject of my talk. I would like once again to stress that here the ball, which is shown here like tunneling, is not a particle. It's a superconducting order parameter. It's a macroscopic wave function which describes the whole microscopic object, macroscopic object. So what about thermal fluctuations? Firstly, the issue was considered in late 60s, early 70s of the previous century. At that time, the smallest and the narrowest superconducting objects were so-called superconducting whiskers. These are single crystals naturally grown on the surface of some superconductors, for example, tin, and they measured the resistance versus temperature. The plot is shown here. So vertical scale is logarithmic scale of the resistance, and horizontal scale is temperature counted from the critical temperature. So 0 corresponds to critical temperature. And within the transition width of about 1 millikelvin, the resistance drops 5 orders of magnitude, but still the width of the transition is not 0. and it is perfectly described by the model of thermal fluctuations, which has been nicely approved by these experiments. I would like also just a little bit to entertain the listeners that actually such tin whiskers you can easily find at home. If you have some old, for example, tin toys, like some soldiers or teaspoons covered with tin, which has not been touched for some time, look at very strong light with some loop at it, and you will see as if a small grass is growing there. It is exactly these tin whiskers, which in the cross-section are about 1 micrometer, but lengths can be as long as 1 millimeter. So at these early stages of studying one-dimensional superconductivity, experimentalists spent days and days picking up a single whisker, making contacts to it and study. Now I'm shifting to another issue about quantum fluctuations. The subject was around already for a couple of decades, and to my knowledge, the most consistent theory has been proposed by Andrei Zaikin and collaborators at late 90s, beginning of the 20th century. The theory is quite complicated, and I'm obviously not going to speak about details. The most important is the last rectangular, which is written here, that the rate of these quantum fluctuations is exponentially proportional to certain quantity, where sigma is a cross-section of the nanowire, Tc is the critical temperature, and rho m is the resistivity in normal state. So if one wants to study this effect, one should fabricate structures with as small as possible cross-section sigma, of low Tc superconductors, no high Tc at all, and which are additionally bad conductors in normal state. So that is why mainly I will speak about low Tc superconductors in my presentation. So first experiments on this subject appeared at early 90s and are mainly attributed to Nicola Giordano, who studied several nanostructures made of indium and noticed that there are so-called low temperature tails, which are attributed to quantum fluctuations. But more precise search in literature shows that already a year ago in the same group where he studied his PhD of group of Danes, they already observed such tails at the bottom of the transition and noted that the role of quantum fluctuations at this time is not known. A couple of years later, again in the group of Danes, they observed very strange superconducting transitions which were not tending to zero resistance even at lowest temperatures, but they did not attribute this effect to quantum fluctuations. And the big punch to this topic was made in the group of famous Professor Tinkham, and at that time his PhD student Alexei Bezryadin used very elegant superconducting technique. They used a non-conducting carbon nanotube, suspended it and used as a substrate, and then they covered it with molybdenum germanium, which is superconductor, and they observed the strange dependencies which are shown here, that not all of them were extrapolating to zero temperature resistance. So that was the beginning of our study when we decided that we have to make something new and more precise. So as I told to you, we used our technique specially developed for this topic to progressively reduce the cross-section of some nanowire. Of course, we fabricated many structures, and all of them, they show the similar dependence. Let us, for example, for concreteness, look at the left image. This is the resistance in logarithmic scale of aluminum nanowire as a function of temperature. And just reduction of few nanometers in cross-section dramatically changes the shape of the resistance versus temperature dependence. 15 nanometers, 13, 12, 11. And as you might see, for the thinnest nanowires, the resistance is not extrapolating to zero if we go to zero temperature. For aluminum, it appears that the characteristic scale is about 15 nanometers and smaller, where this effect should be considered. For titanium, which has even higher normal state resistance and lower TC, the characteristic dimensions are much higher, about 35, 40 nanometers. So it is much easier to study this phenomena in titanium. And already quite, let's say, not too much long ago, we observed the same effect in a more exotic superconductor, niobium N, which also showed very broad transition, which can be attributed to quantum fluctuations. So to conclude this part, I thought I convinced you that in the very narrow superconducting wires, resistance versus transition doesn't extrapolate to zero resistance, and it is the effect of this quantum phase slips, which I was speaking at the beginning of my talk. Obviously, this effect of quantum fluctuations should be observed also not only in nanowires and should manifest itself in other samples, like, for example, nanorings. So let me remind that if we take a macroscopic superconducting ring, the flux is quantized there. And the dependence of energy on magnetic flux in units of superconducting flux quantum is a periodic function. Quantum state with vorticity equal to 0, second parabola vorticity equal to 1, 2, 3, and so on, so far. So if the sample can freely go from one state to another, it might go very high in energy and then jump to the ground state. Again, high in energy and again in ground state. So the transition might have a large periodicity in magnetic flux. However, if the system always goes along the ground state, then it will be sawtooth behavior strictly with one fluxon periodicity. The question is, when the system will finally go from one quantum state to another one? The answer is given on the second plot. When the current, which is the derivative of energy by flux, will be equal to critical current, then the current circulating in the loop will be big enough to suppress superconductivity and system goes to ground state. So that was about macroscopic loop without any superconducting fluctuations. Later it was shown that if now to consider that inside our loop the walls are sufficiently narrow and the quantum fluctuations do exist, then the gap opens in energy dependence. So if now to fabricate a loop with sufficiently thick walls, we should first obtain the dependence of critical current as function of flux, sawtooth behavior with large periodicity. But then when we start to reduce the cross-section of such wire, quantum fluctuations come into play. First, the period should drop to 1, but then also the amplitude should drop. And what is even more important, which is a qualitative effect, there will be reduction of the period of oscillations. So here are our results published in Nature Publishing Group Scientific Reports in 2012. So we fabricated superconducting loops of our beloved material like aluminum and titanium, and then we measured tunnel current here and here. And it is known that it is possible to show that tunnel current in the loop is proportional to density of states, and the density of states itself is proportional to current circulating in the loop. So measuring tunneling current, we can recalculate it into circulating current. And here are our structures. First structure, which has sufficiently thick walls, no fluctuations. And then after several cycles of ion milling, it becomes much narrow. So when the walls were thick, we have a huge amplitude of oscillations of current with large periodicity. Then the period starts to be stochastic. And then finally, when we go to quantum limit, the periodicity starts to be strictly one flux period, and the shape is not anymore sawtooth, but it starts to be degenerated sinusoidal type. And the same effect has been observed in titanium, even on larger scales. So to conclude these two parts, for both effects, like resistance and persistent currents, we should obtain the influence of superconducting fluctuations on its property. And these are so-called integral properties. So one should have an extended sample to measure resistance, or extended loop to measure persistent current. But now let us again come back to the issue of quantum fluctuations, or on fluctuations in general in a superconducting system. Do you hear me? Hello?
Yes, you can.
I can hear you very well.
Great. So, superconducting order parameter is a complex value which has modulus and phase. And as I tried to convince you, both the modulus and the phase can fluctuate. So if to plot, let's say, energy as a function of time, so it fluctuates along some wire corresponding to mean field order parameter, but from time to time it rapidly drops to zero and then again fluctuates. And this process is accompanied by abrupt change of the phase by plus minus 2 pi. And particularly these type of fluctuations I mainly discussed before, quantum phase slips. But as you might see, there are also small fluctuations, these ripples. And these are so-called Gaussian fluctuations, and I'm going to speak about them. And our theorists were capable to show that when the Gaussian fluctuations of the phase happen, it renormalizes the electronic states, which leads to initiation of plasmons, or charge density waves, which propagate along superconducting wire. They're called so-called Muir-Shon mode. And then they renormalize the superconducting density of state. The plot shows how the density of states is renormalized as function of temperature. At zero temperature, it is classical BCS, density of state. But when the temperature is non-zero, but still can be very, very small, much smaller than superconducting energy gap, we have superconducting states inside the gap. So formally, it can be attributed to broadening of the density of states, which is typically described by phenomenological Dines parameter gamma. So now we decided to test the same structures, titanium nanostructures, where we can measure the resistance of each nanostructure, for example, as function of temperature. But each of the titanium nanostructure overlaps with a massive superconductor aluminum through a tunnel barrier. So within the same structure, we can measure both the integral property, let's say resistance of nanowire, and also its density of states due to tunneling between superconductor 1 and superconductor 2 through a thin superconducting layer. And these are local parameters because they characterize the density of states and superconducting order parameter just within the interception region, which is just few hundreds of square nanometers. So first, the extended integral properties, resistance versus temperature for two titanium nanowires. And as and in before experiments, for thick sample, the superconducting transition is rather sharp. For very narrow sample, it's broadened and it's not going to superconducting state. So superconducting fluctuations do manifest itself as I showed to you in the beginning of my talk. Now, it is the same characteristic obtained on interception between the same nanowire and massive aluminum. So the insert shows the derivative of IV characteristic, and it shows that the IV characteristic of the tunnel junction is only slightly broadened compared to a macroscopic IV characteristic, which you can find in any textbook of superconductivity. And indeed, we show that the density of states is broadened, and our IV characteristic can be nicely fit by the model produced by Andrei Zaikin and co-workers. And also, just if to zoom the IV characteristic, we show the Josephson current, but its magnitude is much smaller than what would expect from Ambigar-Baratov expression, and it is exactly again due to fluctuations. So what is the explanation now? Here we again have to discuss some theory. It appears that in the issue of superconducting fluctuation, there are characteristic parameters. First is called G psi, which is the ratio of superconducting quantum resistance, which is 25.8 kiloohms, to the resistance of a superconductor in normal state of the length psi. The smaller is this parameter, the more close to superconducting fluctuations we have. For bulk samples, R psi is big, and then no quantum fluctuations is observed. And this parameter is mainly responsible for the first part of my talk I was going to speak about. But then these events, due to quantum fluctuations, exchange with this plasmonic mode, Muishon waves. And this is already a collective phenomena, which is characterized by another dimensionless parameter, which is again the ratio of the same quantum resistance to the impedance of the system. And then our theory showed that the whole story goes along this line. What is so-called characteristic length scale, which exponentially depends on these parameters. And we call it X index C. So if XC is much smaller than the length of the wire, then the Cooper pairs are localized and the system cannot show integral superconducting properties. But if the length of the system is smaller than this Xi, then the system shows some superconducting properties, like, for example, superconducting gap with broadened density of states. I again want to express that this exponentially strongly depends on the cross-section. So just few change on nanometers of the same nanowire might bring it from one limit to another. So now I conclude on physics. I have 10 minutes left. So what I tried to convince you that superconducting fluctuations is a basic phenomenon which suppresses zero resistance, persistent currents, and smears density of states at energies about superconducting energy gap. So what about applications? How this phenomena can be used for future nanoelectronics, mainly superconductors? First, and probably the most spokeable application, is so-called qubit, quantum bit. I will not speak a lot about this. As all of us know, the classical bit is the system where it has only two states, 0 and 1. But in quantum mechanics, all possible superpositions are possible. And this forms the basics of quantum computation and quantum communication, the superposition of different quantum states. This topic became extremely popular during the last decade. There have been numerous suggestions how to realize quantum bits. I'm not going to expand on the subject, but my personal opinion that for the moment, the only scalable system which can be seriously considered, these are qubits made in superconductors. And there are mainly two approaches. One, where the quantum parameter is the number of Cooper pairs on small island, and this is called charged qubit. And another, it's a persistent current in the loop, typically split by Josephson junction, so it is split, where the quantum parameter to be in superposition is the circulating current, clockwise or anti-clockwise. Everything works okay, but those who work with quantum computers have permanent problem with dephasing. And it appears that this dephasing mainly comes from these tunnel junctions, here and here or here. That there are so-called two-level fluctuators within tunnel barriers, which suck energy from the system, which destroy superconducting superposition on long time scales. Some time ago, it was suggested that this effect of quantum fluctuations or quantum phase slips can be used to construct a quantum logic of a new generation. So it's a massive superconducting horseshoe shortened by a narrow superconducting wire in the limit of quantum fluctuation. The energy gap, the energy spectrum is shown here. It has a gap between consistent states. And the results was published by us in 2 paper scientific reports in Nature in 2012. So indeed, it was possible to demonstrate that quantum phase slip phenomena can be used for building a qubit. Next interesting application, various Coulomb effects. Here is the artistic representation of several IVs dependent on current, on voltage. For a conventional superconductor, massive one, or Josephson junction, the voltage drop is 0, but still there is a supercurrent. What I'm going to show you, if now we study the very narrow superconducting wire in the regime of these quantum phase slips, a small gap opens, and if additionally the wire is very narrow and the environment is very high ohmic, we will get a Coulomb blockade. So it's really something ridiculous. Still it is superconducting nanowire, which has hundreds or maybe thousands of atoms in cross-section, but still it shows Coulomb blockade. So current is not going unless you apply sufficiently high voltage. Why it is so? Again, theorists are capable to show that the Hamiltonians of both systems of Cooper pair box, which is shown here, and our superconducting system where there is an island connected to external circuit with these very narrow nanowires, are dual. It meaning that these systems should show exactly the same behavior with substitution of parameters. So parametrically they are equivalent. Or in simple words, conventional system with tunnel junctions has localized tunnel junctions here and here. And in our case, this phase slip effect is a dynamic equivalent of this tunnel junction. But there is one complicity for experimentalists. If one wants to study fluctuations of phase, which is quantum conjugated variable to charge, one should stabilize the charge. It's just the uncertainty principle. And stabilizing the charge meaning that you have extremely good current biasing. And it is not sufficient just to put a good current source on top of your refrigerator. You should stabilize the current by the proximity of high ohmic electrodes. So in this generation of samples, we fabricated a very narrow titanium nanowires with high ohmic bismuth electrodes. And some of the electrodes has the resistivity as high as 10 megaohm. And then we studied IV characteristic of several subsequent parts of these titanium nanowires. And all of them indeed showed the Coulomb blockade. So it's sufficiently small voltages, the current is not going. It is insulating state of a superconductor. The amplitude of this Coulomb blockades oscillates as a function of the gate applied to nearby electrode and disappears above the critical temperature of the system. So it is indeed something related to superconducting state. It's not just a conventional Coulomb blockade. And finally, the last issue I'm going to share with you is so-called quantum standard of electric current. Let me remind you, and this is taken from the lectures for my students, that currently in SI system, current is one of the 7 principal units. So all electromagnetic quantities are described through definition of ampere. But the very definition comes from the early 20th century and is defined by Ampere's law. 2 infinitely long wires should be placed at a distance 1 meter, and a force density of 1 meter of such a extremely narrow nanowire should be equal to a certain value. It's easy to say, but it is extremely inaccurate to measure. That was okay at the turn of 19th or 20th century, but not now. So it appears that fabrication of quantum standard of electric current is just an outstanding challenge for modern quantum metrology. And again, I show you the same Hamiltonians showing that Coulomb blockade and quantum phase slip are quantum dual characteristic. So everything which is observed in conventional Josephson systems can be observed in superconducting nanowires in the regime of quantum fluctuations. So if in a Josephson junction we have IV characteristic like shown on picture A, then when we apply external radio frequency radiation, we see singularities at quantized position of voltage. This is very well-known Shapiro effect, which is in the basis of quantum standard of voltage, and it is actively used all over the world. In our dual system, we have a rotated IV characteristic which shows Coulomb blockade. If now we apply high-frequency radiation, following this duality, we should have the quantized steps of the current, and this is now our objective. So again, we fabricated a sample, titanium nanowire, very narrow, to be sure that it is in quantum fluctuations, and it was surrounded by very high impedance arrays of Josephson junctions. The IV characteristic is shown here, this IV characteristic without any external electromagnetic radiation. But when we apply radiation, some singularities happen at positions indicated by the arrows. And on the next step, I show the derivative of this IV characteristic in units of current normalized by charge of Cooper pair times frequency. So it's a universal relation showing that indeed there is a quantized steps in such system. And if to plot the position of these quantized steps, they really follow the expected linear dependence. So it's proof of principle demonstration of the quantum standard of electric current. However, they are not as sharp as desirable. So far we managed to obtain accuracy of about few percent. And for quantum metrology, it should be at least 10 to minus 7. So that is the prospects for the near future to improve the accuracy of these quantized steps. So I'm now coming to the conclusions. What I wanted to tell you that reduction of a superconducting cross-section turns it into quasi-one-dimensional region. And it appears that in this limit, the properties of a superconductor exponentially strongly depend on fluctuations. So for sufficiently narrow superconductors, these quantum fluctuations are capable to suppress zero resistance, suppress persistent currents, and broaden the density of states. So it's not anymore BCS density of state. The quantum dynamics in these systems is dual to conventional Josephson system. So everything which has been observed in Josephson systems can be obtained in these systems, but without undesirable Josephson junctions, which are static in space and time. Here we have a dynamic equivalent of a Josephson effect, which leads to very interesting phenomena like Coulomb blockade or single electron transistor. And if now to synchronize this process of quantized current going through such a system, we can obtain the dual effect to Shapiro, which might serve as a basics for new generation of quantum standard of electric current. Thank you for your attention.
Thank you very much, Konstantin. First of all, I would like to thank very much your amazing talk with several scientific news and very didactic presentation. Before starting the question session, I would like to do the propaganda of our network. And for this, I will speak about the members of our Latin American physics Latin American network. The Latin American network, LAFMAT, is composed by some universities in South America and research centers. One of them are Universidade Nacional Maior de São Marcos, in Peru, Universidade Federal de Pernambuco, Brasil. Universidade Federal Rural do Rio de Janeiro, também Brasil. Universidade Nacional de Colômbia, Civenstave, México. Universidade Nacional de San Martins, Argentina. Universidade de Zulia, Venezuela. Universidade de São Sebastião, Chile. Universidade Católica de Chile também. Thank you very much again, Konstantin. And I have one or two questions, and I will call others to question you. My first question is about your presentation about the persistent currents, and the answer for this persistent, you show graphics looks like little park effects.
Yes.
What is the difference, or it is only the origin of the little park? Because your studies show that the transition from one minimum to another minimum is because the quantum fluctuations. Is it the answers of the little park effects?
Yes, thank you for a very nice question. Yes, of course, it is the very generic link with little Parkes effect. What is little Parkes effect? You fabricate a superconducting loop or a hollow cylinder, apply magnetic field, and measure the resistance very close to Tc. And you obtain periodic oscillations with period exactly to one flux quantum. And on this diagram, it corresponds to situation when system goes from nth state to plus minus n+1 state. So the system always goes on the ground state. But if one would be capable to measure little Parkes effect at very low temperatures, then the periodicity might be much higher than one flux quantum, because system might go to metastable state. And we use this phenomena just to qualitatively show that the reduction of the cross-section of the little Parkes loop goes to another limit. Now, what about the quantum fluctuations? Quantum fluctuations open the gap in the spectrum, in meaning that now the persistent current as a function of magnetic flux is not like in little Parkes effect sawtooth, but it has much smaller magnitude and it is sinusoidal. That is the answer.
Oh, thank you. And the second question is about the Shapiro steps. Really, the Shapiro step, the origin of the Shapiro step is the oh my God, I forgot the name now. But we have the uniform Shapiro steps when you have a normal Joseph's junctions. What's the origin of this very no anomalous Shapiro steps in your work? I didn't understand. Of course, you told, but I cannot understand.
The formal answer is the following. If you look at these two Hamiltonians, first is for QPS and second is for Josephson junction. They're identical with the substitution of parameters. So flux is interchanged with charge 2e. So when in conventional Josephson junction you apply high frequency radiation, it is synchronized with the transmission of charge 2e, which gives this conventional Shapiro effect. In our system, which is dual, where the phase fluctuates, it synchronizes with the frequency produced by external radiation. And this is, as you called, anomalous or dual Shapiro effect. So instead of voltage, you have current steps.
Mm-hmm. Okay, thank you very much again, Konstantin, for your talk and your answers. And I will invite here to ask you, Professor Mauro Doria.
Hello, Konstantin. How are you?
Hello, alive still.
Thank you very much for your very pleasant talk and interesting and enlightening. I want to ask a question, perhaps for my own understanding. I mean, these phase fluctuations are caused because the coherence length is larger than the cross-section, the diameter of the wire, so to speak, correct?
Correct. But I would say that the word because is not the right. It happens in the system which are one-dimensional. Because the whole model is only for one-dimensional system with cross-section smaller than the coherence length. But fluctuations happen because the order parameter is a quantum field which fluctuates in space and in time.
But don't you have a crossover if you have a, say, wire such that the diameter is larger than the coherence length? Then these phase slips begin to disappear. Is this observable?
I would say like this: if the cross-section is larger than the coherence length, we are not anymore in the one-dimensional limit. So there might be parallel channels of current and the physics is completely different. But interesting thing that we can be at the limit between standard thermodynamic fluctuations and quantum fluctuations. For example, on the left image, the thermodynamic fluctuations are shown with dotted line and solid lines are shown for quantum fluctuations. So for sufficiently thick nanowires, but still one-dimensional, you can observe standard thermodynamic fluctuations. And for very narrow, quantum start to dominate.
Okay. I have another question connected to this. Is because, I mean, in your talk, you don't address the mean free path in the normal states. And I find that this is a parameter that is useful to understand the physics. For instance, if how the diameter of the wire compares with the the normal state mean free path. Because if you have that the mean free path is larger than the diameter, then you could have even quantized levels, I mean, inside the wire, normal state, because the electrons, they are really trapped into some kind of well with definite wavelengths, and you have a physics that is clean. I mean, even in the normal state. And if the mean free path is smaller than the diameter, then the electron has collisions, I mean, in the orthogonal direction. I'm worried mostly about the orthogonal direction, and the physics changes, should change dramatically. I mean, and the mean free path usually can be obtained because if you multiply it by the resistivity, it gives a constant number. Rho times L gives a constant number. So, I mean, I would like to understand, because I think that there is another crossover set by the mean free path. I mean, usually these materials have a mean free path of 50 nanometers or 10 nanometers, and that should change the behavior. I mean, if you have a wire which is a diameter of 100 nanometers or 10 nanometers, don't you think so? Or
obviously, you are absolutely correct, but short answer that this is the subject of my next talk, because I really studied this effect in a clean limit superconductors, which is the, let's say, thickness of a superconducting film is comparable to the mean free path. And there we do observe the quantum size effect when the energy is quantized, density of states is quantized. That's true, absolutely true. But in this work, we're mainly working with dirty superconductors, where the mean free path is at the level of 10, 20, 30 nanometers, where the cross-section of the wire is of the same order or larger.
Okay.
But there are no intergrain boundaries. So it's a polycrystalline structure, but relatively pure. And this effect is observed irrespectively of what is mean free path. It's universal phenomenon.
Okay, thank you very much.
Thank you, Konstantin, again. And now a question from England to Russia. Stuart, your time.
Thank you, Konstantin. Very interesting talk. You gave us a lot of information. I didn't get all of it. You mentioned tin, the possibility of studying tin. Now, I'm interested in tin, the semiconductor form of tin, but you can get the beta tin inclusions. Are we likely to see the same type of behavior that you have explained in perhaps a disordered tin wire that has maybe alpha and beta tin?
Well, obviously, as I just told, the effect of fluctuations is a universal phenomenon, and it should be observed at all superconductors. But as I showed the formula, here it is exponentially depending on critical temperature and normal state resistivity. So tin has TC about 3.7, and resistivity of tin, if it is not very dirty, is much lower than resistivity of titanium. So my prediction would be that this phenomenon can be observed at tin, but you should go to sub 10 nanometer scales. It's just a very, very rough estimation. But if you are interested in fluctuations in general, as I showed, and I again showed the subject, the first effect of fluctuations, but thermal fluctuations, were observed in tin whiskers. But here it's a very small broadening of resistance versus temperature, just 1 milli-K. In titanium nanostructure, we have broadening about tens of and hundreds of millikelvin, which is much larger effect because of its low TC. That's it.
Thank you, Konstantin. Very, very interesting. Thank you for your comment there as well.
Thank you, Stuart. Thanks, Stuart, for your question. Mauro, you would like to talk or any other thing?
I would like to make just one last question. I mean, out of curiosity, is it possible to work with whiskers made of bismuth? Because bulk bismuth has a very large mean free path of order of 2 microns, 1 micron. And perhaps it would have interesting properties, I mean, associated to this large mean free path. I don't know if this is...
You're absolutely right. Bismuth is a very interesting metal because it has anomalously low Fermi energy, 28 milli-electron volts, and in some particular directions, it has very small effective masses, 10 to minus 3 or free electron mass. So quantum phenomena in bismuth might be obtained at sufficiently large scales. And we indeed observed the quantum size phenomenon in bismuth, but not in whiskers. We observed it in a single crystalline nanostructure, which we fabricated on the surface of mica, which has exactly the same lattice constant as bismuth. But I know the group, and even I studied some samples from them, where they fabricate bismuth single crystalline nanostructures, nanowires. It's a nanowire of bismuth, let's say cross-section of about 100 nanometers, 200 nanometers, and it can be centimeters long. And this nanowire is encapsulated in glass. So in this, yes, in these objects, quantum phenomena are very, very pronounced indeed.
Interesting. Thank you very much for your answer.
Thank thank you again, Mauro, for your participation. And Angel Bustamante. Angel Bustamante.
Yes, of course. Professor Konstantin.
Angel, can you open your webcam?
I hear very well.
Yeah, okay. This is what, yeah. My question is about over temperature. You show in the range, millikelvin range. Quantum fluctuation and this experiment is only in range the millikelvin, or you have, for example, a temperature of helium liquid, or how many range is the this effect there is?
Okay, thank you. I understand your question. I repeat again that this is a universal phenomenon and it can be observed in any superconductors below its critical temperature. However, it exponentially depends on critical temperature. The lower the critical temperature, the more pronounced is the effect. That is why we worked mainly with low TC superconductors, but not always in millikelvin. For example, now I show the plots. Do you see them? Hello?
Okay.
Yes. So the scale here is 1, 1.1, 1.2, 1.3 Kelvin. And already we have the effect of fluctuations. So if you go to superconductors like tin or niobium, you might observe the effect as much higher temperatures. The only problem would be that then you have to go to extremely narrow nanowires, few nanometers in cross-section. And here we work with 10, 20, 30 nanometers. That's the point.
Okay, thank you very much.
Okay, thank you, Angel, for your question. Thank you, Konstantin, for your answer. Ximena, do you have any questions?
Good day, Professor Konstantin. In this moment, I have a problem with my camera. I'm sorry.
Yeah.
But now I don't have question. I think that the topic is so interesting. Thank you for the talk. And you don't have question also in our university. Thank you for the talk.
Okay, thank you, Ximena. Eliane Marcela, do you have questions? Okay. Eliana.
Hola, perdón, muy buenos días. No, en este momento no tenemos preguntas del público. Gracias por el espacio. Solo agradecimientos por la charla.
Okay, thank you very much. Eliana doesn't have questions. So I don't know if I forgot any other panelists, but if possible, Konstantin, can you close your slides?
Yes, okay.
And
now.
So people can, if possible, open your webcams to thank you, Professor Konstantin. Oh, thank you, Stuart. Angel, go to Icha Ceviche. Okay, thank you very much, Professor Konstantin. Again, thank you very much for your interesting talk, and hope to see you in Lima.
Yes, I would be very happy to come at the conference. Mario told me that there will be a conference in October.
Yeah.
So is it possible to attend it?
Of course. I suppose the information is in the web page of the LAFMAT. If you don't have this link, I can send for you or Mauro.
Yes, I already looked at it, and even I shared it with my colleagues, and they are very much interested in coming.
Yeah. Oh, nice.
There should be an invitation, formal invitation, perhaps. Yes, let's talk to Luis. I think Luis is on travel, but we should arrange.
And I have some colleagues which work with interesting phenomena like spintronics, topological insulators in superconductors also. So if you are interested, you may invite them for the seminar and then to the conference, whatever is appropriate for you.
It will be very great.
Konstantin, I think that we should find a way to send invitations for you and for those that want to come to Lima.
Yes.
Soon. I mean,
No, it can be done in this week because Luis is coming, and so he can write invited letter for you. There is no problem.
Thank you very much. With pleasure.
Okay.
So, thank you again, and see you.
See you. Bye-bye. Thank you.
Thank you. Bye-bye.
Bye.
Okay.
Bye.